For decades, aging was modeled as stochastic damage, but Geroscience now defines aging as a regulated biological progression controlled by specific nutrient-sensing networks. The accepted protocols for extending lifespan during middle age are remarkably consistent. Practice caloric moderation, lower your dietary protein intake, and suppress cellular growth signaling. The objective behind this midlife restriction is to maintain insulin sensitivity, optimize metabolic efficiency, and minimize cancer risk by keeping cellular repair mechanisms active. However, a clinical paradox emerges in later life. If you maintain these exact nutritional interventions into your late 70s, they predictably accelerate frailty and increase mortality risk. This graph shows the physiological risk profile across a human lifespan. The optimal protein and growth signaling output remains flat through midlife, but at approximately age 65, the body's requirements sharply reverse direction. The optimal diet for longevity is not static. Applying the restrictive metabolic rules of midlife to a late-life body is a clinical error that actively drives physical decline. The standard recommended dietary allowance, or RDA, for protein is currently set at a baseline of 0.8 grams per kilogram of body weight per day. Strict adherence to this 0.8 gram standard after age 65 becomes a primary driver of sarcopenia, the age-related loss of skeletal muscle mass and immune senescence. Reaching centenarian status requires moving beyond these baseline standard guidelines. To understand why, we must decode the dynamics of the mTORC1 signaling complex, the quantitative thresholds for the amino acid leucine, and the mechanobiology of our vascular system. Surviving into your 11th decade requires reverse engineering the Centenarian phenotype and restructuring the precise molecular signals we feed our cellular machinery. Every cell in your body constantly scans its environment, measuring available energy and nutrients before making the biological decision to grow or conserve. This diagram illustrates mTORC1, the Master Metabolic Switchboard. It integrates energy and amino acid signals through control gates like Raptor and Pras40. Operating on a binary balance, active mTORC1 drives cellular growth, while suppressed mTORC1 triggers autophagy and mitophagy to clear damaged proteins. During midlife, age-associated hyperactivation of mTORC1 is highly pathological, linking directly to cancer-promoting growth and metabolic dysfunction. Continuous growth signaling suppresses autophagy clearance. This effectively clogs cellular maintenance systems with misfolded proteins and damaged organelles, accelerating senescence. Clinical interventions like caloric restriction and the drug rapamycin extend health span in model organisms precisely because they force the suppression of mTORC1. During our middle decades, suppressing the cellular desire to grow is a critical biological defense against metabolic decline. As humans cross the 65-year threshold, the physiological priority shifts from whole-body metabolic scaling to the maintenance of skeletal muscle. Older adults develop a condition known as anabolic resistance. This is a state where aging skeletal muscle progressively ignores the presence of dietary protein in the bloodstream. In a younger individual, a modest meal easily triggers robust muscle protein synthesis. In an older adult, that exact same meal produces a severely blunted response. Overcoming this resistance requires exposing the muscle to a drastically higher concentration of essential amino acids. The critical variable is leucine, which functions simultaneously as a structural building block and a unique biochemical signal to initiate translation. The aging body maintains its capacity for muscle synthesis. It has simply shifted the chemical threshold required to initiate the process. Identifying the trigger for this response requires looking inside the cellular cytosol at cestrin-2, a protein that functions as a high-fidelity amino acid sensor. In low leucine conditions, cestrin-2 binds and restrains the Gator-2 complex, keeping mTORC1 shut down. High leucine concentrations bind cestrin-2's hydrophobic pocket, triggering a physical conformational shift. Cestrin-2 releases Gator-2, which then allows RAG-GTPases to recruit and activate mTORC1, initiating muscle protein synthesis. Translating this microscopic mechanism into practical Gero-nutrition yields a strict mathematical threshold. older adults must consume approximately 2.5 to 3.0 grams of leucine per meal to trigger this specific conformational shift. Hitting that target requires ingesting 25 to 40 grams of high-quality leucine-dense protein in a single setting. This explains why standard low RDA diets, or grazing on small amounts of protein throughout the day, often fail older adults. Hitting this exact per-meal leucine dose is a mechanical requirement to bypass anabolic resistance and prevent physical frailty. While preserving muscle mass gets you to age 85, surviving into your hundreds requires conquering a second pillar, the cardiovascular system. In standard aging through the 70s and 80s, the dominant cardiovascular threat is subclinical atherosclerosis, or plaque buildup. But for the oldest old, the pathology shifts. In extreme old age, the primary threats become heart failure and microvascular dementia, which are driven by cumulative myocardial remodeling rather than simple blockages. This is driven by vascular mechanobiology. Physical changes in the artery wall, like elastin degradation and collagen cross-linking, increase arterial stiffness over decades. This physical stiffness alters the shear flow of blood. The resulting mechanical stress forces endothelial cells to release inflammatory signals, accelerating aging in the brain and heart. This dashboard compares biomarker data. NT-proBNP is a peptide released during myocardial wall stress, a biomarker for heart failure. Notice the chronically elevated levels in standard octogenarians. However, exceptionally surviving centenarians exhibit starkly lower NT-proBNP levels, even when accounting for other risk factors. The Centenarian phenotype is defined by structurally elastic microvasculature. This physical resilience absorbs the mechanical stress of a century of heartbeats, protecting cardiac output and brain function. Achieving exceptional longevity demands that we abandon the concept of a single, static diet for human health. This diagram maps nutritional strategies across stages. Stage 1, ages 20 to 65, uses caloric moderation to suppress mTORC1. Stage 2, from 65 to 80, flips to structural preservation, requiring a protein increase to at least 1.0 grams per kilogram. The success of this stage relies on aggressively targeting the 2.5 to 3.0 gram per meal leucine threshold to force cestrin-2 activation. Stage 3 represents the centenarian transition, from 80 to 100 and beyond. The directive shifts to maintaining high nutrient density amidst declining appetite, while monitoring and preserving endothelial vascular health. Extending the human health span is a calculated pivot from growth suppression in midlife to targeted anabolic support and vascular compliance in later life. By actively manipulating precise nutrient sensing thresholds and preserving mechanical vascular elasticity, we move past a generic concept of aging and enter the era of precision Gero-nutrition.